Deep inside the Sun's outer atmosphere, a game-changing discovery has emerged. New measurements from the Parker Solar Probe reveal a phenomenon called the Helicity barrier, which alters how turbulent energy turns into heat and may finally explain why the corona reaches millions of degrees and how the solar wind accelerates. In this video, we'll uncover what Parker actually measured and explore why this breakthrough transforms our understanding of our star and similar plasmas across the universe. The breakthrough revolves around the Parker Solar Probe's daring mission into the Sun's low corona, where environments are extreme and collisionless. Parker, launched in 2018, has become the closest spacecraft ever to the Sun, passing within just a few million miles of the solar surface and sampling plasma in the very region where long-standing mysteries like the coronal heating problem and solar wind acceleration originate. In this near-Sun domain, particles hardly collide, and magnetic forces rather than collisions drive the behavior of plasma. Until now, much of our understanding of how turbulence dissipates in such conditions has remained theoretical. What the team discovered is that turbulence does not always act like a smooth cascade of energy from large scales down to small scales, where it dissipates into heat. According to the standard theory, large eddies break into smaller eddies, eventually becoming heat via collisions or wave-particle interactions. However, Parker's in situ measurements of the magnetic energy spectrum in the solar wind revealed systematic changes in slope and curvature around ion scale lengths, exactly when certain plasma conditions hold. These deviations match predictions of a phenomenon called the Helicity barrier. The result is direct evidence that when the barrier is active, the turbulence stalls or is rerouted rather than simply dissipating as expected. The paper, led by Jack McIntyre, PhD student, and supervised by Christopher Chun at Queen Mary University of London, shows that the barrier appears under identifiable conditions, and that under those conditions the spectral shape is altered in a way that no other mechanism had cleanly predicted. This strengthens the case that the Helicity barrier is not a fringe idea, but a mechanism that's been active in the Sun's youth wind all along. What makes this particularly exciting for a general audience is how tangible the result is. Rather than a vague, maybe turbulence heats the Sun, we now have numbered thresholds where the mechanism flips on. Parker's measurements give this smoking gun signature. The spectrum changes when plasma beta and wave imbalance cross those thresholds. That means the discovery is not just descriptive, it's predictive. As more Parker passes gather data, scientists can now test exactly where the barrier activates, how strong it is, and what fraction of the heating goes into ions versus electrons. A key point of this discovery is that the Helicity barrier doesn't operate under all circumstances. It is activated when very specific plasma conditions are met. The first of these conditions is that the ion plasma beta must drop below approximately 0.5. Plasma beta is the ratio of particle thermal pressure to magnetic pressure. A beta of 0.5 or less means the magnetic field's influence dominates the motion and dynamics of the plasma. In this magnetically dominated regime, particle collisions are infrequent. The geometry of field lines is important, and wave-particle interactions tend to shape behavior rather than simple fluid dissipation. The second condition involves the normalized cross-helicity, a measure of the imbalance between waves propagating sunwards and those away from the Sun. The researchers found that when this cross-helicity exceeds about 0.4, the barrier becomes increasingly prominent. The interpretation is that when turbulent waves are strongly imbalanced, more in one direction than the other, the usual cascade of energy through interactions of counterpropagating waves weakens, and a barrier to further cascade can form. With both conditions satisfied, beta less than 0.5 and cross-helicity greater than 0.4, the magnetic energy spectrum around ion gyroradius scales, the length scale at which ions circle magnetic field lines, shows a distinct flattening or feature rather than the standard power law drop. This spectral signature corresponds to the barrier. The cascade of energy to ever smaller scales is inhibited or diverted, and instead energy may be transferred through alternative channels, such as ion cyclotron waves or selective ion heating. Because ions in the solar wind are often hotter than electrons under these conditions, this captures observations that standard turbulence alone struggled to explain. The fact that Parker finds these threshold conditions frequently near the Sun makes the barrier a candidate for a major controlling mechanism rather than a niche effect. In the inner solar wind, where the probe spends its time, magnetic pressure tends to dominate, and imbalanced flows are common. Thus, the barrier may be a pervasive player in shaping the heating and acceleration of plasma. For the audience, what's remarkable is this: the sun's environment isn't just hot and crazy. It meets the exact criteria for this mechanism to operate, and Parker measured it. We now know when a kind of switch flips the turbulence behavior into a different mode. Understanding the helicity barrier is important for two major realms: space weather and broader astrophysics. First, on the space weather front, the behavior of the solar wind, how fast it blows, how much energy is carried, how ions are heated, matters for satellites, communications, power systems, and astronaut safety. If the barrier changes how and where energy is deposited in the solar wind, it affects how models predict high-speed streams, ion heating, and magnetic fluctuations reaching Earth. Second, the astrophysical implications are profound. Many astrophysical plasmas, from the interstellar medium to the hot halos of galaxies and the accretion flows around black holes, are collisionless, magnetically dominated, and turbulent. The helicity barrier offers a template for how energy dissipation works in these systems. Under low beta and strong wave imbalance, energy may divert into specialized heating channels, rather than a simple cascade to heat. Additionally, the discovery enriches how we think about the coronal heating problem. For decades, scientists have sought a single explanation for why the corona is so hot. The helicity barrier doesn't replace all mechanisms, but shows that conditional mechanisms exist, ones that activate when thresholds are crossed and that lead to different heating outcomes. The Parker Solar Probe's discovery of the helicity barrier marks a turning point in solar physics. It reveals how turbulence converts energy into heat, solving a decades-old mystery about the sun's blazing corona. This breakthrough deepens our understanding of plasma behavior across the universe and advances accurate space weather prediction. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration. Thank you for watching, and see you next time.